Thanks a lot for the invitation, the opportunity to give our first Colloquium talk of the year. Yeah, in this series, in this series, the staff series, and yeah, in the immortal words of Mark Twain, I didn't have time to prepare a short talk, so I prepared a long one instead. Those of you at my SAMS talk, this is an extended version of my talk at SAMS. Right, so I work in the intersection of mathematical physics and topology, and with a hefty dose of category theory. And specifically, I work in the area of topological quantum field theory. And despite the name, this is actually a branch of pure maths, which uses techniques inspired from quantum field theory, i.e. physics. Compute invariance in low-dimensional topology. When I talk about low-dimensional topology, I mean I'm talking about surfaces, three-dimensional manifolds, knots and links, four-dimensional manifolds. And today I want to speak about one aspect of this work which I found particularly beautiful and which is sort of a focus of my research at the moment, in particular, 3 of my students. Namely, the way many finite-dimensional complex vector spaces in maths can be profitably recast in a geometric framework. So there's this nice dictionary which I'm going to spend the first half of the talk explaining between linear algebra and geometry. So in linear algebra, we have the concept of a finite-dimensional complex vector space. And in geometry, we have the concept of a holomorphic line bundle, L, over a compact complex manifold, M. And I'll explain what those terms mean in a second. This dictionary goes further. An inner product on the vector space is going to correspond to, on the geometric side, something called a fiber-wise inner product on the line bundle. And the linear map between vector spaces is also going to have its analog level of geometry. That's going to correspond to something called a holomorphic section, i.e. a kernel of the product line bundle. Right. So let me explain the stuff on the right-hand side, since I think we're all familiar with the stuff on the left-hand side. So I want to talk about the category of line bundles and kernels. It's not something that's sort of written down in the literature. It's something that I sort of, the way I organize the data myself. So a complex manifold of complex dimension n is a topological space M equipped with a covering UI of open sets and local charts, which are homeomorphisms of those open sets onto a neighborhood in Cn. That's where the n comes from. And transition functions, to say that's a complex manifold, we demand that the transition functions are holomorphic. So what do I mean by that? So I've got some topological space M. Think this would be a one-dimensional complex manifold, 2-hole donut in this case. So you cover M by local charts, and each chart is a homeomorphism from that open set into an open neighborhood in Cn. N is 1 in this case. And so yeah, I've got another chart of a different section of M. And the demand that we make is that these coordinate change maps must be holomorphic bijections. Is that clear? Okay, that's what a complex manifold is. A holomorphic line bundle over a complex manifold is a collection of one-dimensional complex vector spaces vary holomorphically with X. So they're indexed by the point X in the base manifold M. Just to be more precise here, that means, what do I mean to vary holomorphically? I mean that there's a complex manifold structure on the total space, so the collection of all these lines. You put a manifold structure on that, and the manifold structure is not some random one. It's such that there's a covering of M by open sets, such that when you restrict L to that covering, you just get a product. So just the picture here, just keep in mind, if you zoned out there, I've just got now a collection of one-dimensional complex vector spaces. That's why I say it's a line bundle. Complex line is a one-dimensional complex vector space, parameterized by the points in the base space M. Okay? Just to say a little bit more, yeah, we've got obviously the projection map from the line bundle onto M. And a holomorphic section of the line bundle is going to be a holomorphic map from the base space into L, such that pi after S is the identity. That just means that it's going to send an element Z in the base space. It must land up, S of Z must land up in the line living above Z. Okay? So for every element in the base space, then we've got these vectors in this one-dimensional complex. 5 is living at that point. So that's what a section is, and that map must be a holomorphic map. And we write gamma of L for the vector space of holomorphic sections of L. It is finite dimensional if the base manifold M is compact. I should have added that. So that's sort of abstract nonsense, that if the base manifold is compact, then this vector space of holomorphic sections is going to be a finite dimensional vector space. So that's where this dictionary has started, between line bundles and finite dimensional complex vector spaces. Let's do some examples. Yeah, I'm doing the tangent bundle of S2, but I suspect I'm going to run out of time, so I'll leave this for the interested people afterwards. Let's do a next example. So this is a sort of canonical example. So I've got my base manifold M is the 2-sphere, and the line bundle is going to be what's known as the tautological line bundle. So what do I mean by that? Well, I should really say this comes from the holomorphic diffeomorphism between the 2-sphere and CP1. CP1 is the collection of all one-dimensional complex subspaces of C2. Right? So that's where this line bundle is really living. So we call it tau, TIF, or tautological. And it's just a nice fact that CP1 as a manifold identifies with S2. So we'll rephrase things in terms of the 2-sphere later, but for now, just think in terms of CP1. So a point in CP1 is a line in C2. So this red thing is a point in CP1. And associated to every point, I want to associate a complex line. That's what a line bundle is. So associated to this red thing, which is a point in CP1, what line am I going to associate to it? The line itself. Right? So that's why it's called the tautological line bundle. Okay. That's clearly a sort of extremely canonical line bundle that you can write down. And yeah, when you make the identification between the 2-sphere and CP1, then you can, that means above every point on the 2-sphere, I've got this line bundle, or this complex vector space, and you can actually sort of draw a nice picture for what these vector spaces look like. Yeah. Okay. So I'm just giving examples of what a line bundle is. A line bundle is just a bundle of lines on a manifold. At every point in the manifold, we have a one-dimensional complex vector space. This was the example of the tautological line bundle over CP1, i.e. S2. Okay, what's the vector space of holomorphic sections of this line bundle? In fact, this guy doesn't have any holomorphic sections. So this guy, all it's got is the 0 vector space. But you can correct that if you look at its dual line bundle. So that would be associated to every point. Instead of taking this line, I take the dual, the linear dual of this line. The linear dual of a vector space is mapped from that vector space into ground field C. That guy does have holomorphic sections. And in fact, if you tensor power that line bundle, so given a line bundle, I can form its tensor powers. The holomorphic sections of the dual of the tautological line bundle tensored up k times as a vector space is a k plus 1 dimensional vector space. Okay, so that's a way to generate any k plus 1 dimensional vector space as sections of a line bundle. You can always use this projective space line bundle. Here's another example for nice example of line bundles for someone like David. I know he's interested in elliptic curves. We're going to have a seminar on Friday where he will speak about elliptic curves, right? So yeah, our base manifold M is the complex plane modulo a lattice. And our line bundle is going to be a certain thing that I'm going to construct. So here's the complex plane. And by a lattice, how I'm going to construct a lattice, that just means a discrete subgroup of C. And I'm going to construct it generated by 2 vectors, the vector 1 and the vector tau, which is just some vector. And then I take integral linear combinations of those that spans out a lattice. And then I take the quotient space. The quotient space is then going to be a torus because you can identify opposite sides. Right? So I take C modulo this lattice, I'm going to get a torus. And the line bundle I have to describe to you. So a point in this quotient space would be an equivalence class of points, right? So that all those black points together, that's a single point in the quotient space. And I have to associate a complex line to that. You think of that A as being an orbit under this action of the lattice. But what complex line am I going to associate to this point? Well, it's sort of an ugly definition, but this just comes out of classical mathematics from the 19th century. What you do is all those black dots, I'm going to associate a single one-dimensional complex vector space, namely the vector space of all functions on those black dots, which satisfy these two equivariance properties, that when I move across by one, the value of the function doesn't change. So when I move in the direction of the one generator, when I move in the direction of the other generator, the value of the function picks up this factor in front. Okay, and it's clear that such a function would be determined by its value on just one of those black points, and then it would be uniquely extended everywhere. So that's why it's a one-dimensional complex vector space. And yeah, so that gives us a line bundle over the quotient of C by this lattice. And the holomorphic sections of this line bundle is a one-dimensional vector space spanned by Riemann's theta function. Yeah, there's a formula that you can write down. Yep. Where? This one is Z plus 1, and below it's Z plus tau. Yes. No, it's because I've made a mistake. That should be f of z. Thank you. Yeah. Thank you. Okay. So there's this cool thing that Riemann wrote down in the 19th century, but they just thought of these things as sort of certain holomorphic functions on the complex plane. But now I'm recasting it as a holomorphic section of a line bundle. Okay? And the space of sections of this line bundle will then be the space of functions on the complex plane having these properties. Anyway, that's a one-dimensional vector space. Take-home message here. You can generalize this to have a line bundle where you say, okay, I want the functions to have this equivariance property when now capital N is some positive integer, and then the sections of that line bundle will be an n-dimensional vector space. That's the space of theta functions of characteristic n, and this is something that Dario is working on, just so that you know. Okay, so now that you understand what holomorphic line bundles are, I want to describe an equivalence of categories between, well, between the category of vector spaces, finite dimensional vector spaces and linear maps, and the category of line bundles. So this thing on the left, an object is a finite dimensional complex vector space V. So I'm describing vect, not vect-op, just vect. And a morphism is just a linear map. One thing to remember about linear algebra is that linear maps from V to V prime is canonically isomorphic to the dual of V tensored with V prime. Right? What is this category on the right? So an object here is a holomorphic line bundle over a compact complex manifold M. And a morphism from one line bundle to another line bundle is a holomorphic kernel. In other words, it's a section of the product line bundle living over the product. So just to have a picture of that, yeah, I've got a line bundle over M, and here's a line bundle over M prime. What do I mean by a morphism between them? I mean a section of the product line bundle, and when you write out what that means that for every x in M and every x prime in M prime, I'm going to have a linear map from Lx to Lx prime. You can think of that as a matrix indexed by M cross M prime. That's why it's clear that it's kind of like a matrix. But now the cool thing is that the indices of our matrix are continuous variables, whereas a normal matrix has got just finitely many entries. But they're continuously many entries here, but they're all correlated because it has to be a holomorphic section. So having finitely many entries and having continuously many, but being correlated by saying that it's holomorphic is the same thing. Okay, now I was late for this talk because I've made this error before. I don't usually phrase this thing this way, so I got a little bit stuck in my category theory here. There's a slight problem with the contravariance of this functor. I don't usually phrase this way. I usually take it one level further where there's an inner product when you can make this a covariant functor. But at this level, it has to be contravariant. And there's a slight bug in the ointment here. But anyhow, let's just go through this. So how does this functor work? So from a vector space, I'm going to construct a line bundle. How do I do that? Take my vector space, finite dimensional vector space, and I just output this tautological line bundle over a projector space, at least its dual. That's the line bundle I associate to a vector. And one thing to note is that the holomorphic sections of tau dual is canonically isomorphic with V. That's where you get this contravariance coming through. Sorry, that's an error. It's canonically isomorphic with V dual. Sorry, not V. Yeah. So the point is that every vector space can be viewed as a vector space of holomorphic sections of a line bundle. That's really cool. You come across a complex vector space in practice, you're walking on the road, you hit one, and then it can be thought of as sections of a line bundle. In some situations, that's a very profitable way to think about it, because then you can analyze it through using geometric methods. Similarly, for a linear map, then, from A from B to V prime, I'm going to give you a kernel here. So that would be, what is that? If you just do your abstract nonsense, that means I have to associate it to every line in V prime, a map from that line to a line in V. And what you do is you take the original map A, you take its dual, and you restrict it to L prime. Yeah, it's sort of all abstract nonsense, but it works out nicely. So that's the functor going forward, and then the functor coming back is going to, what do I do to a line bundle? I just take its space of holomorphic sections. That's how I turn a line bundle into a vector space. And similarly, you can turn kernel into a linear map. And yeah, so that's a very pretty dictionary between linear algebra and geometry. Whenever you go from algebra to geometry, you normally have to do an op, and that's why there's an op over there. And this dictionary goes much further. So for example, if A is a linear map from a vector space to itself, you can compute its trace on the geometric side by calculating a certain integral. It's really handy, right? It gives you a bunch of tools in your toolbox. But to do that, we're going to need another concept called the Bergman kernel, and to that we're going to now turn. Okay. So this now ties in with what I was talking about at SAMS. So let's talk about the Bergman kernel. And to introduce the Bergman kernel, I want to first, instead of talking about it in the context of complex manifolds, let's talk about it in the context that we should all know about, namely complex analysis, functions on the complex plane. So what does the Riemann mapping theorem say? 1851, a very important theorem in complex analysis, says that let U be a simply connected open set in the complex plane. It doesn't have holes. Then there exists a holomorphic bijection from that U into the standard or into a disk. Right? And moreover, how does this bijection work? We can make it unique. Once you pick a starting initial point in the open set U, then phi is unique if we demand two things, namely we want to send Z0 to the origin, and we want the derivative of phi at Z0 to be 1. Then that fixes it. So this is a wonderful theorem because it tells us that open subsets, any simply connected open subset of the plane is holomorphically isomorphic to any other one. There's no interesting invariance there. And it exactly tells us how to construct, well, it tells us the uniqueness of that isomorphism as well. This is really handy, can be used in all sorts of ways. So it's almost, not exactly, I would say the fundamental theorem of complex analysis is Cauchy's theorem, but this is a really fundamental theorem in complex analysis. But a question arises, yeah, if you remember when you covered this work, maybe you did it in honors or something, is that it's always done from a very abstract point of view. It's like, it's an existence result. But the question is, can we write down an explicit formula for this phi? And I want to show you that the things I'm talking about today, coherent states and Bergman kernel, actually give you a nice way to treat this Riemann mapping theorem. So I'm motivating them through the Riemann mapping theorem. Okay. So Bergman in 1950 wrote a nice book where he defined this thing called the Bergman kernel of a bounded domain in the complex plane. Just be this function here. So it's a function of 2 points and in the domain. And all you do is you just take a sum of all orthonormal basis of holomorphic functions on that open subset. So that'll be, you just take a basis of holomorphic functions. Orthonormal, what do I mean by orthonormal? There's an inner product on functions because I can, giving one function another function, I can integrate their product over that region. So that gives me an inner product on functions. And that's what I mean by being orthonormal. And you just construct this sum. Okay. Let's do an example. So suppose U is our favorite region in the complex plane, just the unit disk. What would be a orthonormal basis of functions there? It's just the standard functions z to the n. They're actually all orthonormal. And I've just got to take into account, I've got to normalize them by this prefactor. So if I then sub this formula in there, then I just calculate, and I'm going to get out this summation here, which I can rewrite in this way. So that's the Bergman kernel on the unit disk. It's often sometimes called the Poisson kernel. Complex analysis. That's true, right, Dana? Yes. Okay. Okay, well, what can you do with this Bergman kernel? So in that book, Bergman wrote down a wonderful thing. He said that the Riemann map, which identifies an arbitrary, this thing that we were trying to write down, a holomorphic bijection between an arbitrary simply connected open subset U and a disk D, can be computed explicitly as follows. So yeah, I'm wanting the one that sends Z0 to 0. So I picked that initial point Z0, and then the question is, where does an arbitrary point W get to? And here's explicit formula. It's written down in terms of the Bergman kernel. You take 1 over the value of the Bergman kernel at Z0, comma Z0, and then you've got to do an integral along a path from Z0 to W. Which path? Any path. Why does it not matter? Because it's simply connected. So Cauchy's theorem says that integral along any path give you the same answer. If there was holes now, then we would have problems, right? Of this expression here, just the Bergman kernel evaluated at Z0, comma Z. So I integrate along this path. I think that's really cool. So that's an indication that Bergman kernels are cool because it gives you an explicit formula for the Riemann map. So from a different viewpoint, given this domain U in C, define the coherent state based on Z0 to be this holomorphic function. So I fix Z0 now, and then I can think of the Bergman kernel, which used to be a function of 2 variables, right, Z and W. If I fix the one variable, Z0, then I've just got a single variable function. And we call that the coherent state based at Z0. So it's a certain holomorphic function associated to Z0. And it can be characterized as the holomorphic function on U, which is maximally peaked at Z0. In other words, any other holomorphic function, its norm at Z0 must be less than or equal to what psi is times this. I should have put absolute value there. Anyhow, so in sort of physics lingo, it's the delta function at Z0 expressed as a holomorphic function. Okay, so when U is the unit disk, what are these coherent states? So to any point in the unit disk, I have a canonical and important holomorphic function, the coherent state based at Z0, which I can just use my formula for the Bergman kernel from the previous slide, and this is what it will be. So thought of as a function of W, it's going to be this function. This is a complex function, but I can always draw a graph of its norm, and it's going to look like this. Note one important thing here. I said it's the function which is maximally peaked at Z0, but this guy doesn't sort of go up to Z0 then go down again. But that's because if you know remember from complex analysis, holomorphic functions satisfy the Laplace equation, right? And so what that means is that their norm have no maxima and minima. The maximum and minima can only occur on the boundary. Okay, so it would be impossible to have a sort of a peak at Z0 right here. But on a compact manifold, this can happen. This is not the open disk is not a compact manifold. The reminder to Bruce, do your Mathematica demo here. Also, heads up, you're halfway through your slides. Okay, that's so I spent an awful lot of time over the weekend being really stupid and trying to do a cool demo. I didn't quite manage to get it right. But, and unfortunately, I've noticed that my Mathematica has just crashed. But anyhow, see. This work. So here I've got this, trying to give you a visualization of this coherent state on the unit disk. So to every point in the unit disk, I have this holomorphic function associated with that point. And it's the sort of holomorphic function which is maximally peaked at this point. As I drag this point around, holomorphic function changes, right? So these are the coherent states on the unit disk. Each point I've got a different function. That's right. The color represents the argument, and the height represents the magnitude. It's just from this formula. You can see the formula over here. 1 over pi 1 minus yeah. So we're thinking of that as a function of W. It will be like if my Z naught is real, then W will be real on the real axis as well. Just from that formula. Yeah. Okay. So that's coherent states on the standard unit disk. But now what if I take some cool, interesting region in the plane? What are its coherent states? Okay. So I thought since we had an amazing talk, Nitex talk on Monday by Pietra. What is it? Pietra gave the talk on Monday, right? On the mathematics of love. Okay. So it was a good talk, yeah. And so I thought, let's take the heart as our region in the plane. Okay. So we need an equation for the heart. There's a nice implicit equation up there. I want to picture the same thing now, the coherent states for the heart. Okay. So how do I do that? The only thing you need to do to calculate this Bergman kernel is that you need to get an orthonormal basis. So what that means, I can just take the function Zn and just chuck them into this heart and then use the Gram-Schmidt process to orthonormalize them. By the inner product, I'm going to be integrating their product over the heart. Okay. So I do that here. I do, say, 10 vectors. Takes a little while. But yeah, for example, is the orthonormalized process. So the first orthonormal vector is just the constant function 1. Then the next guy is this function. Next function is this function, z squared plus something z plus something, and so on. This is z cubed plus something z squared, and so on, right? These are my orthonormal basis functions on the heart. That allows me then to construct Bergman kernel. And it crashed on me. I was supposed to be able to drag this point around. Unfortunately, that crashed. So, but anyway, this is the coherent state for a certain point on the heart. I don't know where. Okay, it's going to look like that. What I also wanted to then do was actually explicitly construct this Riemann map from the heart to the unit disk using Bergman's formula. And I was getting somewhere, but it didn't quite get the final answer. Okay. Any questions on that?
What was that question in the colorful part?
So what this is, yeah, I put a certain coherent state somewhere, maybe like over here, and then this is just the graph of that complex function that's defined on the hot. It won't have singularities. This is a different way of charting a complex function, where you do your argument on the right, and then the magnitude is the brightness of the color. The argument is the color, and the magnitude is the brightness of the color. There will be zeros. Okay. There won't be poles though. It's a holomorphic function on the hot. It's not. There won't be poles, but there will be some zeros. Possibly. I don't think there. Be zeros. I mean, you can't have that there'll be 1 0. I think. Okay, you're right. You're right. There will be a number of zeros. They're perfectly symmetric. Okay. Well, you're right. So let's check out where exactly are these zeros. That's where the love has died, right? The zeros. I could use this coherent state to then construct a biholomorphism of the unit disk. First of all, I need to construct the coherent states. The coherent states are the tool that you use to make that's the thing that you integrate over to construct the biholomorphism. That's what I was trying to do next, but that got a bit stuck there. Okay, let's just say this. So how do we think about these coherent states? So we can expand any holomorphic function, obviously, as a linear combination of the basis vectors. That's clear. That's always true. But similarly and more geometrically, the coherent states, you can think of them as forming a continuous basis for the holomorphic functions. Namely, in the sense that any holomorphic function on U can be expanded not as a sum now, but as an integral linear combination of them. Right? And the coefficient of psi z, where z is now a point in this disk, is exactly the value of f at z, actually, if you calculate this. So it's like you can't get more canonical than that. We've got an integral, we're expressing f as an integral linear combination of certain things, and the coefficient of that thing at the point z is exactly the value of the function at z. Okay, anyhow. And let's now generalize this whole setup to compact manifolds. So this bounded domain, U, is going to be replaced by a compact complex manifold. Okay. It's both more complicated in that it's a manifold, but simpler in that it's a compact space, whereas this is not compact. So the basis functions here, there's only going to be finitely many of them, whereas here there were infinitely many. A holomorphic function on that complex domain is going to be reinterpreted as a holomorphic section of a line bundle. So instead of associating a number to each point in U, we're going to associate a vector in a one-dimensional vector space. Right? A machine which associates a vector in a one-dimensional vector space for each point in X is almost like a function, but not exactly, right? Because I haven't identified that one-dimensional vector space with C. So I can't identify the value of S at X with a number. I can't say it's an element in a one-dimensional vector space. Okay. The inner product on holomorphic functions on U just goes over to, we just integrate, instead of integrating over the domain, we integrate over X, and now I need on every fiber, I need a fiber-wise inner product on this one-dimensional vector space. So then I get a number which I can integrate over the manifold. Okay, so now I can define this thing. Whereas before I had the Bergman kernel for a domain in the complex plane, now I've got the Bergman kernel for this line bundle. So how do I define it? Exactly the same formula as before. So what do? I take an orthonormal basis for the vector space of sections, and I form the same expression that I did before, the sum over phi I bar times phi I. And I just got to interpret what those phi i's are, but you can do that. So at the end of the day, let's just be clear here. The way that I'm interpreting it here is I'm wanting to still think of it as a function. So what is B a function of? It's a function of two variables. Those two variables are nicely thought of as living on the on the unit circles at each point. So to every pair of points x and y, above x, I've got the one-dimensional complex vector space associated with x, and living inside there is the unit circle. And similarly over here. And then I want to think of b as a function of pairs of points on those unit circles. Okay. So at the end of the day, although it's sort of quite complicated, to any pair of points in a complex manifold, there's a certain canonical thing which I can calculate. It tells you how related those points are. Okay, and similarly, the coherent state based at a point x is just going to be where you fix the one slot. And so now I had a two-variable function, and I fixed the one slot, and I can think of it as a one-variable function, in this case, a section. It's going to be the holomorphic section of L, which is maximally peaked at a certain x. Okay, you can alternatively think of it in terms of linear functionals. I'm going to skip over that. I'm losing some people here, so I'm just going to skip over that. I think there's a nice picture coming up, so maybe I should skip to the picture. Okay, so let's do let's compute this Bergman kernel. So here let's do our favorite example of a line bundle with the two-sphere, i.e. CP1, and our favorite line bundle is going to be the dual of the tautological line bundle, its kth power. So here's a picture. Here's the two-sphere. Living above the two-sphere at each point of the two-sphere, I've got a certain complex line. And we know what that complex line was. It's the tautological line. And living inside that line, there's the unit circle in that line. Okay? And when you calculate that for S2, the collection of all these points, i.e. pairs consisting of a base point x and a point P in the unit circle living above x, that's going to be a three-dimensional space, right? Because there's two dimensions here, one-dimensional in the unit circle. If you write that out, that's just the three-sphere. Okay, so this P, which is where the Bergman kernel is going to live, is actually the three-sphere. By the way, that means that when we restrict our line bundle to the unit circle, we're going to have a map from S3 to S2. And that's going to actually, this map in this case is called the Hopf vibration. So just if you've heard of the Hopf vibration, it lives in the tautological line bundle. Okay, so what I want to calculate here, this is a theorem with myself and Nzaganya, PhD students. Just a first calculation we did was that to compute this Bergman kernel for the tautological line bundle over CP1, it has been computed before, but we are expressing it in a neater way, namely, remember P and Q are points in S3, so it'd be nice to calculate what the Bergman kernel does when I think of P and Q as living in S3. And in the end, what it turns out to be, it just turns out to be, take those points P and Q, they're living inside S3, that means they're living inside C2, so I can take their inner product as elements of C2. And it turns out that's all the Bergman kernel calculates. Yeah, so that's a nice formula. The Bergman kernel is basically the inner product on C2 in disguise. Okay, I had a nice picture here, but it didn't make it into these slides. But it was on the, let me just rewind here. It was the opening. No, I understand where the picture's coming. It's coming in a second. Okay. So now I want to talk about coherent loop states. I've spoken about coherent states. The coherent state at a point x in the manifold is just a function which is maximally peaked there, a holomorphic function which is maximally peaked. Now I want to talk about coherent loop states. So what I want to do is I'd like to form an integral linear combination of coherent states along a loop. So I've got a loop in the manifold, and I want to sort of make an integral linear combination of coherent states around that loop. Let's just be clear what I'm saying. Here's my manifold X. I've got a loop in X. At each point in X, I've got to pick a vector in the space of holomorphic sections, and I want to sort of add them all up around gamma to get a new vector. So I want to integrate over gamma of the coherent states at each point along gamma. How do I do this correctly? I have to know, remember the coherent state is indexed by a point P in the unit circle. So what points P must I choose? And if you do this correctly, what you've got to do is you've got to parallel transport P using the geometric data here. So you can't just choose those P of T's randomly. You fix them at, you fix a choice of P of t at one point, and then at any other point in the loop, the P of t is obtained by parallel transport. Okay. So that's how I can form a coherent loop state. And if you then think about this, what you'd really want is that when you parallel transport around the loop, you'd want to get back to where you started. Otherwise, this integral, the value at naught and at capital T is going to be different, and that's going to cause problems. So we naturally led to the requirement that we want that parallel transport around the loop gamma to be the identity. Okay. So we can make this definition. So suppose parallel transport around our loop is the kth root of unity, and this is known in the literature as being a Bohr-Sommerfeld loop at level k. Then we define the coherent loop states at level k to be this integral that I've just written down. So let's just recap. Associated to points in the manifold, I've got a vector, the coherent state supported at that point. Now associated to a loop in the space, I've got a loop state associated to that loop. Okay. Given by integrating those coherent states around the loop. And then a theorem of Zaganya's in his thesis is that a loop at height, so let's work this out. When will parallel transport be the identity in our example? So we've got our two sphere, and we've got this line bundle over it. And the theorem says that, so if we consider our loops to be the ones that are going at a certain height, then only certain of those loops will have the property that parallel transport around that loop the identity. And the theorem identifies those as precisely the ones that occur at certain discrete heights. Okay? So those are the Bohr-Sommerfeld loops. And then the next theorem is that the corresponding coherent loop states associated to those loops are precisely what physicists call the angular momentum eigenstates in quantum mechanics. So yeah, physicists write down things like this when they're studying angular momentum. These are vectors in a certain vector space. They don't really have a geometric understanding of this. They sort of wave their hands a bit. But in the end, this is algebra for them. But yeah, we're giving a concrete geometric interpretation for these vectors as being the coherent loop states associated with these loops in S2. Okay. What's nice about this parameter K is that, remember, this is the line, this parameter K is in the power of the line bundle. As K gets larger and larger, the support of that coherent loop state localizes onto the loop. That's the key property, right? The support meaning where is the section sort of appreciably non-zero. Okay, and so that really helps when you're calculating inner products of these things, because you know that the support localizes onto the loop. So that was the picture I wanted to show you. This, for example, would be the coherent loop state, which a physicist would write down that vector as the J equals 50, K equals 35 angular momentum state. Now we've got a concrete picture for it as a loop state. What I plotted there is the norm, the fiberwise norm of this loop state. You can see for high values of J, it's sort of concentrating on that particular loop. Okay. Any questions? I think I've got 10 minutes left. Or... Yeah. Good question. It was sort of a combination. So, yeah, so what I want to tell you in the talk is that coherent loop states are wonderful things, okay? Let's write Vk as the holomorphic sections of the kth power of the tautological line bundle over S2. This is a geometric description of the unique irreducible representation of SU2 of dimension k plus 1. So SU2 is a three-dimensional Lie group, and you can look at its irreducible representations, and you're going to have one for each dimension. And we can realize those vector spaces as being these spaces of holomorphic sections. So that gives you a nice picture for these vector spaces. You could also calculate these things algebraically, but this is a geometric way to calculate these things. So a natural problem in maths is to calculate the matrix elements. So an irreducible representation of a group, or a representation of a group associates to each group element a matrix, like a linear map from a vector space to itself. It's a representation of the group. And we'd like to calculate the matrix elements of that representation explicitly. And in the language of physics, they would call this calculating the Wigner matrix elements. Okay? So we're sort of doing a rotation by an angle beta, and then you have to calculate this matrix elements. So Wigner was the father of group theory in physics in the 1950s. In those days, physics and maths were still quite separate. And Wigner was one of the first to bring abstract maths into physics. Like Einstein brought sort of differential geometry into physics. And then, but still, physicists were okay with that, but they didn't want any other stuff. And then Wigner said, well, I'm going to bring in group theory. And in the early days, physicists didn't like that. They called it the group pest, because they didn't like this new abstract math. But now this is now classical stuff. Every physicist deals with this. Okay. Anyhow, the physicists Littlejohn and Yu wrote down a beautiful asymptotic formula for these matrix elements in a physics-style paper. So they didn't give a formal proof of this formula, but what they said was that for large J, these matrix elements compute according to a certain formula. And so let's just understand what this formula is saying. What they said is that reinterpret these things as sort of loop states, so associated to M and M prime. You've got these two loops. And then you rotate the one loop by beta around the y-axis. So then you're going to get this situation. And then we can calculate the area enclosed into there, that blue area. And what their formula said is that essentially the matrix elements computes as the cosine of that area. It's a really cool geometric formula. Okay, so theorem with Zaganya is that their formula, once you correct it because they made some typo or some error, is actually indeed correct. So we can prove it just using this technology. You end up having to calculate this double integral, and then this double integral you can then approximate using the stationary phase calculation. You get their formula. Okay? So in fact, some mathematicians now, Borthwick, Paul, and Uribe, established a general formula for the asymptotics of the inner product of any two coherent loop states for any line bundle over a Kähler manifold. And what they said was that the inner product of two coherent loop states can be expressed like this. There's a certain sum which involves over points in the intersection of the two loops. You've got to calculate a certain thing that you can calculate at every intersection point. And their proof is very complicated, and we don't understand it. It uses a result of Boutet, de Monval, and Guillemin, and we don't understand it. Okay. So what we're doing is we are giving a different proof of that using a more elementary method, namely the stationary phase formula. Okay. But the input there is you have to calculate. You have to calculate a certain Hessian, and we're busy calculating that Hessian. Yeah. So let's summarize. This talk was titled Coherent Loop States and Their Applications, and it's an important theme in my current research. So the present work in this area is joint with Nzaganya. Is that the angular momentum eigenstates in physics can geometrically be interpreted as coherent loop states. This leads to a stationary phase proof of Littlejohn and Yu's geometric formula for the Wigner matrix elements for large M. So that's one thing. Another thing that we've done is that we've given a stationary phase, or we're busy giving a stationary phase proof of Borthwick, Paul, and Uribe's general formula for the inner product of coherent loop states in arbitrary Riemann surfaces. Yeah. That's as far as Zaganya's project goes. In future work, joined with Dario, wanting to do a higher dimensional, use a higher dimensional generalization of coherent loop states to higher dimensional manifolds. Then it won't be a loop, but like a surface, to give a new and natural isomorphism between two descriptions, so between the skein space and the holomorphic sections descriptions, the vector space assigned to surfaces in Chern-Simons TQFT. The TQFT means topological quantum field theory, as I said in the beginning. Anyway, there's this thing in the literature where there's two descriptions of the same vector space. It's known that these vector spaces are isomorphic, but the isomorphism is written down in an ugly way. And yeah, we're going to use coherent loop states to give a nicer description of that isomorphism. Okay, some other things I'm wanting to look at in the future is to use coherent loop states to rederive known formulas for the asymptotics of the classical and quantum 6J symbols. Since these can also be expressed as inner products of sections of line bundles over certain modular spaces. So these are certain things that mathematical physicists compute. And as long as it's expressed as an inner product of loop states, then we can apply our stationary phase technology to it. Okay? Some other future work, I want to describe addition of angular momentum in physics explicitly in this geometric framework. In other words, to compute the holomorphic kernel associated to Wigner's 3J symbol linear map. Don't worry, that's big mouthful. It's just an interesting, cool thing. When you study angular momentum in physics, in the end, you have a sort of physics model for the addition of vectors in three-dimensional space. And the amazing thing, according to quantum mechanics, if I take a vector of length J1 and another vector of length J2, and I ask physics to add those vectors together, it doesn't produce the head-to-tail addition exactly. It actually, when you add two vectors together, you're taught in primary school that or not primary school, maybe grade 12 or something, you stick the one vector at the end of the other vector, right? What quantum mechanics says is that there's actually a probability distribution for the answers that can come out. And the most probable will be that answer. But there's actually a distribution. And I'd like to calculate that distribution explicitly. It can be done in this framework. So that's some future work. Also study modular forms in this framework. So modular forms also can be expressed as sections of a line bundle. The moment your vector space can be expressed as sections of a line bundle, then the technology of coherent loop states comes into play. Okay, and so one specific question I want to look at there is, there's a nice linear map when you're studying modular forms, which is really important in the world of modular forms, namely the Hecke maps, right? And as I said earlier, every time you've got a linear map, you can think of it as this kernel. So I want to calculate that kernel that the Hecke maps come from. So there'll be a geometric way of thinking about the Hecke maps. And then finally, also a nice simpler project would be to describe and visualize the coherent states associated to the Platonic solids. It's the cool fact that associated with the Platonic solids, you can form like a algebraic variety and you get a line bundle. Anyway, you should be able to draw some nice pictures in Mathematica here. Okay, so finally, I want to just speak about my students. Let me introduce my students. So this is the most important part of the talk. So who have I got? I've lost some students. Sorry about that. So in the slide that was before this, there were two other students. So that would be Nzaganya. There he is, right there. He's in his third year. He comes from Tanzania. He is an assistant lecturer at the University of Dar es Salaam Dose campus. Say again? Muse campus. Okay. So hopefully he'll be submitting end of this year and you've seen what he does. You can go. Thanks for. Oh, they'll need to come in. Nelson is my PhD student in financial maths. There he is here. He did his MSc with Ronnie Becker and myself earlier. He's from Uganda. And unfortunately, Prof. Becker passed away on Sunday. So just say that. And I think Nelson would have been one of his final students. Okay. Then I also have Philippos Sitolidis, who I'm co-supervising at Oxford. Okay, and then I've got a few more students. So Shimal Harichern is a first-year PhD student And Brian McKeary is a master student. Yeah. Thank you.